Hi, gang. Today we're going to talk about securing your data and how to make your applications um, more secure, particularly in an environment where um, many data repositories are being compromised. So we're going to make sure that we're going to try to make sure that at the very least, that our data is not being able to be seen in a clear text manner, meaning that if for whatever reason our data repository was compromised, that the data wouldn't be able to be read clearly um, by an attacker. For instance, if we don't want to store our social security numbers, driver's license numbers, or any other sensitive data like credit card numbers in a clear text manner, we want to obfuscate it, meaning make it unintelligible or unclear or obscure. Before we begin, I want to talk about a great resource here, the OWASP um, project. And here is the site. You can see the URL right up here at the top. And this is the Open Web Application Security Project. It can be used for other aspects as well too, not just for web development. So it's a great resource. I highly encourage you to do some research on your own of OWASP. Okay, um, I have some examples here that I want to talk about, but before I do, I want to make sure that we understand the distinction between encryption and hashing. We're going to be hashing our values, and there's a couple ways of obscuring the data. One is to hash secure data, and the other is to encrypt it. Hashing, and sometimes they're used synonymously. Um, there is a distinction though. Hashing means that we're storing the data in a one-way obfuscation, meaning that the data is is obscured or made unintelligible and cannot be dehashed or unhashed. Once it's stored like that, it cannot be unhashed. But there are other issues with that as well too. Now, number one, it's always stored in the same length, and number two, it always returns the same hash value, regardless of how many times it's run. So that's a problem with that. Encryption, on the other hand, is using a two-way method of obscuring the data. So the data is encrypted and then it can be decrypted with a proper key. And they both have their pluses and minuses. We're going to be using a hash algorithm, and because we're not going to be using any keys for encrypting, so we're going to today we're going to be talking about using hash algorithms. Um, so that's the distinction. Hashing is one-way data obfuscation. Encrypting is two-way. Encrypt it, get a key, and then you decrypt it. Now, in class, I've mentioned and I've given examples of hashing data to make it less easily retrieved from an attacker. But I do want to say, and I only said this in class without any going into any great depth. I just wanted you to be able to mask the data, but really it wasn't very secure. For instance, as I'll give an example here, um, we have this data right here, and you can see that I just doing some generic hashing using the MD5 algorithm, and that stands for Message Digest 5. And somebody used the password ABC. By the way, another good reason why not to use um, simple passwords, because they can be hacked really easily, even if there is a hash algorithm that's used with it. So I'm going to show this here. I got my SQL open, and I'm going to run this hash algorithm, MD5, um, along with the password ABC. Now you see when I run it again and again, it always returns the same hash value, right? And we could see the length of that if we want to. We could just put in here, use a MySQL length function, and to see how many bytes we would have to store it. Because we would have to store it using either char or varchar 32, because we want to store 32 bytes. When you're storing a hash algorithm, always use char, because varchar will use the same exact number of bytes plus one more byte for the length of that field. Well, we don't need to use varchar because we know in a hash algorithm it's always going to return the same number of bytes. Oh, and by the way, if I use, say, SHA-2 using a 512 hash value, um, we're no better with this because it's always going to return this value no matter what. No matter how many times I run it, it's always going to return the same hashed value. A little bit longer, a little bit more difficult to find out what the actual value was of ABC, but nonetheless, it can be found out. Now, how can it be found out? Well, it can be found out through what we call rainbow tables. Rainbow tables. I want to back up just a bit here as well too. Let's talk about these hashing algorithms. So MD5 hashing algorithm, Message Digest 5, has been broken many years ago. I believe it was somewhere around 2004, I believe. I've heard as early dates as 1996 as well too, but I think the official date was 2004. SHA-1 has been officially cracked as well. I believe it was by the Google team that cracked the SHA-1. SHA stands for Secure Hash Algorithm 1. So SHA-1 was compromised, hacked, cracked, if you will, by the Google team. And so the most secure, well, for a number of years, the most secure has been SHA-2. But they say that theoretically, that SHA-2 may be compromised as well too. Now, no one has officially claimed SHA-2 has been broken. However, they say that it's possible, theoretically possible. So they've been working on, I believe, since I think 2006. They've been working on a new hash algorithm called Secure Hash Algorithm 3, which was it's already a specification now. It's a finalized specification as of 2015, August 2015. I'm making this video in 2018 on July 4th, by the way. Our Independence Day, July 4th, 2018. So roughly 3 years ago, August of 2015, that the NIST, and NIST stands for National Institute of Standards and Technology, released a final specification or final version of the Secure Hash Algorithm 3. Now, the reason why I'm saying this is that, interestingly enough, it was the first cryptographic hash algorithm that was a public competition. Now, I don't know if there was some prize money involved in that or not. I think there was. But, you get, even if there wasn't, just to say that you were the winner is going to bring a lot of endorsements, no doubt. So, yeah, it was the first publicly held competition for vetting the new hash algorithm. And again, it went through 9 years of development from 2006 to 2015 before it finally became a specification. So that's SHA-3. The problem with SHA-3 is that it is, at this time, July 4th, 2018, it hasn't been used much in DBMSs, database management systems, or in programming languages, uh, uh, or in public and or corporate development. To be quite honest, even though it's been out for 3 years, it really hasn't been well known or well used, and they need some of the DBMSs will need to come up with their built-in intrinsic functions to handle the new SHA-3 permutation. So going back to this, we still use MD5, as you know that many times you'll get a file and it'll have a MD5 key along with it to find out if that file has been compromised. So they still use Message Digest 5 hash algorithm, but again, it has been broken. So wouldn't it be good to store your data that you want to obfuscate in a database using MD5? The most secure right now that's widely used is Secure Hash Algorithm 2. But there is a problem. As I mentioned to you, that every time that you run a hashing algorithm, it's always going to do two things. It's always going to return the same exact number of bytes or alphanumeric values, plural. It's always going to return the same values, no matter how many times you run it, and it's going to have the same length, the exact same length. Now, when I'm speaking concerning is that MD5 will always return 32 byte value. SHA-2 512 will return a 128 byte value. Now, again, a much more harder to um, find out what that value is, but still it can be found out. Now, how they find that out is the use of rainbow tables. Now, what is a rainbow table? A rainbow table is just really a pre-computed table for reversing any cryptographic hash function. So, for instance, I'm doing a very small example here. Here's a rainbow table containing two values. Okay, the values here are for this is a MD5 hash algorithm hash value that will is based upon the characters ABC. So every time I run MD5 with ABC, it's always going to return this value. Anytime I run MD5 with the value 123, it's always going to return this hashed value. So if you do a quick internet search and you want to find out some rainbow tables, you can get those rainbow tables that have pretty much every pre-computed permutation of all of the hashing algorithms: MD5, SHA-1, SHA-2, 256, SHA-2, 384, hashing algorithm, SHA-2 512. And it's always going to return the same value based upon that hashing algorithm. So that's while it obfuscates the data from a novice attacker, any intermediate attacker would easily be able to get a set of rainbow tables and then find out what that value actually was. And by the way, you're not safe either by doing something like this. Okay, so let's go back to the MD5. You're not safe by, it's better than ABC, but they have these permutations. First of all, what they do is they stick a digital dictionary, say an English dictionary, and get every combination of word used. Now, these rainbow tables are huge. They're vast, but they cover pretty much every word used in a dictionary, and not just English dictionaries, but um, other language dictionaries as well too, and include other variations of, say, passwords. Like, say, someone will come up with a real slick password like welcome, right? Using 3 instead of an E. Well, I promise you, that's going to be in a rainbow table. So when you do do a password, make sure you use alphanumeric values, upper and lowercase alpha values with some type of special characters in there as well too, to protect yourself from rainbow tables, because um, many even administrators, um, maybe not many, but there are administrators that don't protect their data from a DBA standpoint, database administrator standpoint, as well as a network administrator standpoint. So be careful to make your passwords um, less easy to detect. Okay, so what can we do to prevent that? We know that a hashing algorithm does not prevent us um, from someone to backward engineer, if you will, through a rainbow table what the original value is. Again, they can't decrypt the value. They can't decrypt this hash value here that I have for welcome. They can't decrypt that. But a rainbow table would indicate that this value equals this password right here. Okay, welcome with 3. So what we could do to mitigate against that is we can use salt with that. Use salt. Now, what does that mean? That means that along with our hashed value, we're going to include um, some type of data to mix in to salt, if you will, the specified secure data that we want to prevent a user from seeing. One word of caution: don't use the same salt value for all your records, because that, while using a salt is better than nothing and using a hash value is better than saying clear text, you really want to use some type of random salt value for each record, and then store that salt value along with that record. And by the way, when you store that salted value, it's going to be unique for each record, and you could use it for all of the data for that particular record. So if you want to hash a social security number, a user's social security number, their driver's license number, and any credit cards, you could still use that one randomized salted value. So how could we do that? Well, we could do it like this. Here, for instance, I'm using the MySQL random bytes function, and I'm going to use the 64 byte version of that. So I'm going to then just run this so you can see what it is. My bad, that's not in my buffer. Let me try to copy it now and run this. Sorry about that. That was the length. I was going to show that after. So you know now that the length of that is 64 bytes. But here's what it looks like if the data were in fact compromised. And by the way, this is in binary. Command prompts cannot display binary, so that's why it's displaying in this fashion right here. By the way, it's just another means of obfuscating the data by storing it in binary rather than a um, alphanumeric hash value. Okay, so there's what we got. We got our salt. We're going to use random bytes as the salt. And so here's some practice, okay? We're going to create a variable called salt. That's what the @ symbol's for. Salt is the variable with the @ symbol. We're going to store the random bytes that we just generated right here into that variable. And then what we're going to do is we're going to add the sensitive data here. So we say sensitive data could be social security, whatever, right? Patient ID, credit card number, driver's license number, whatever. We're just saying it's sensitive data. Now, I do want to say one thing here. Here is the pseudocode for our solution right there. Now, what we're going to do is we're going to take the sensitive data and we're going to mix that with the salt. And by the way, it really should be this. Okay, we're going to take the sensitive data plus the salt. We're going to concatenate the sensitive data and the salt, and we're also going to then hash that value. So we're taking the sensitive data with the salt, concatenating the sensitive data with the salt and then hashing that value to make it much more secure. Matter of fact, orders of magnitude more secure than just using a, a generic hash algorithm. Okay, so here's a practice. There's our randomized bytes for the salt. There's our sensitive data. What we're going to do now is, again, using concat, the MySQL concat function, we're going to append the salt to the sensitive data and then hash that at the SHA-2 512 hashing algorithm. And then we're going to display it to see what we get. Okay, and here we go. Display this. Sorry about that. It's not in my buffer. It is now. And so I set the variable salt, set the variable sensitive data to ABC. Salt was randomized 64 bytes. And then this value is hashed. I wanted to show you that even though the value was ABC, that you can see that it is a different value that was hashed before for the one for the randomized bytes. Okay, excuse me. For ABC, you could see that this value, which includes the salt, is different from this value. So even with the rainbow table, it would be orders of magnitude more difficult to distinguish what that value actually was of ABC, even if the user used a very bad password like that. Okay, so now all we have to do is figure out what length do we need to store this. Well, we could just run the length function on it. And again, this is not in my buffer, so you have to indulge me here. Let me try this again. And you can see that it is 128 bytes. Well, that's a lot of bytes. Okay, it is keeping our data sensitive data stored. But for every piece of sensitive data, we'd have to store 128 bytes. Now we could use the char data type, char 128, but that's a lot of bytes. Let's try to bring this down a bit, and let's even make it more obfuscated. What do we mean? We're going to change that into a binary value. So we're going to do the same thing. We're going to salt our sensitive data. We're going to concat the sensitive data with the salt. We're going to hash that value, and then we're going to make it into binary. So again, we're making it even more unclear as to what that is. And you can see, again, because command line cannot read binary data, that it's coming out like this, which again makes it even more difficult to discern from an attacker's point of view what that actual data was. Okay, so then we want to find out the length of that. So let's see. The original length that we had before was 128. Oops, my bad. It keeps not storing that for me in my buffer. As you can see, the length was 128, and now we have that. You just saved your boss or yourself 64 bytes for every data item that you want to store, be it social security number, credit card numbers, driver's license numbers, whatever. Okay, so that is the practice. We're going to implement it. Okay, we're actually going to implement it and see how we can use this. Now, I do want to say a word of caution here. Here's my notes here that you could read. Gang, anytime you're doing this over the internet, the first thing you want to, or the network, first thing you want to do is make sure you're on an SSL, secure socket layer connection. So regardless of whether your data is obfuscated or not, the sensitive data can be seen over the network if you don't have an SSL connection. Okay. Now the other thing is that the randomized salts need to be stored so that we can use them later. Like say if a user wanted to use a password that was salted and hashed and put into binary, we would have to store that randomized salt to be able to use it for a future comparison. Um, so here again, rather than providing the same salt for all secure data, in other words, for every record, we're going to randomize the salt for each record. So if for whatever reason that salt happened to be compromised, all the data for every record could potentially be compromised. So doing it like this, giving it randomized bytes for each particular record, makes it, again, orders of magnitude more secure. Okay, so let's begin like this. Let's create a database called hash. Again, I'm not advocating any illicit behavior here. We're just calling this database hash. We're going to drop the database if it exists, create the database if it not exists. Again, as you can tell, line 34 here is really redundant because we already dropped it, but I'm just showing you how to use the if exists, if not exists clauses. Gang, I mentioned it in class. Always use if exists or if not exists when you're creating your databases. The reason for that is this: if you don't use if exists, and I know I'm repeating myself here from what you guys learned in class, but if you just said this, drop database hash, fine, no problem if it existed. If it didn't exist, if the hash database did not exist, and you're running this through an application, your application would crash. Bam, you're done. You'd have to put it in a try catch block, and it would generate an error. If, on the other hand, you used if you used drop database if exists, I'm sorry, I did this backwards. Yes, drop database if exists hash. If you use that, what would happen with your program? It would generate a warning, and the program would continue to run. So the difference between a warning and an error is the fact that the error would stop the application from executing. So what we call an error in programming is an exception. So it would stop the execution of the program, where a warning, it would continue to run. Okay, so drop database if exists, create database if not exists, and then use hash. Okay, I'm going to do that right now, like this. I'm going to do that. Here we go again, not in the buffer. So let me do this right now. Okay, there we go. All right. And I'm using the hash database. And I'm creating a table with 3 attributes. Let's take a look at those. I have a user ID that's int unsigned primary key auto increment, just our generic primary key. And then I have what I call my secure data of social security number. Now notice what the data type is. I'm storing it in a binary version, binary 64. I'm also storing along with that my salt. Now, you guys, this is just for demonstration purposes. Don't name your attributes salt, okay? And probably don't want to have a database called hash either. But this is, again, just for demonstration purposes. You want to always obfuscate the data as much as possible. If a hacker, if an attacker was able to compromise the system and did see an attribute called hash or salt, then it would immediately alert them. So call it something else to try to hide the actual reasons for that attribute. But our reasons are, specifically, I did this just so you wouldn't get confused, is to salt the actual data that we want to obfuscate. Here it's social security number. By the way, if we had 15 other attributes here, credit card 1, credit card 2, phone number, patient ID, driver's license number. We could obfuscate that data as well too using this one salt mechanism that we have here. So we don't have to create another salt. But the beauty about this is that when we actually see how this works, that we're creating a unique randomized salt for each user. Okay, so let's create this database, and I'm going to do this. Hopefully this is in the buffer, and it is. Good. So let's show tables, and we got our user table. Okay, now what's next? Well, the next thing is we're going to I put here for you in comments. Another reason to obfuscate data, because users will choose bad passwords. So we can't stop a user from using passwords like password or test or ABC or 123, but we can at least help them not to get their data compromised. So, and then also we could enforce login parameters to login credentialing parameters to prevent users from doing that. So a good administrator will prevent a user from even being allowed to use a password like that. In other words, force them to use, say, at least the minimum length of an 8 byte or 8 character password, uppercase, lowercase, alpha values with numbers and special characters. So we can do that. All right, so what we're going to do is use the bad password ABC, just as we did in the past. Above, we're going to randomize our salt, 64 bytes. And then what we're going to do is we're going to insert this. Let's take a look at this. Look at this insertion here. Just like a regular insert, by the way, from our first database course, we're going to insert into the user table using those 3 attributes, UID, SSN, salt. We're going to insert this. How does it work? We're going to here concat the salt here with the social security number, the 512 hash value, and include the salt again. So here we're storing the binary version of a salted and hashed social security number. Okay? And we're going to make that, we're unhexing it, so we're going to make it binary. My apologies here. I misspoke. Here is the social security number right here. The hypothetical social security number that we have in our variable SSN. So that is going to be assigned to this attribute SSN. We have to store the salt so that we can use it later on to make our comparison. So there's our salt. That's the randomized bytes right here. Okay, and then of course the UID is just a auto increment, and that's why we use the null value here. By the way, because we created this auto increment right here on line 40, we actually in MySQL we actually don't even need to use this attribute. So we could take this out like this, but be sure if you do that, you want to take out any associated values. The only reason I included it in there is just for demonstration purposes to show that there are 3 attributes. Okay, so let me do this now. I'm going to set a variable, SSN, ABC, set the variable randomize salt, insert that into our user table. By the way, gang, line 45 and 46, you could see that if we're doing an actual web application or any, say, client-server application or any other type of application, we can get user input. Again, it would be a client-server application, some type of client-server application. But we can get that user input. Here, I'm just simulating that by creating these variables. But you can actually allow a user to enter that data. Line 46, of course, line 46 would be something that we generated on the development portion. But line 45 would be something that you can capture from user input. Okay, so we're just providing this social security number, SALT, inserting into the user table, and okay, and let's see what we got. Well, let's go back here and select all from user. And again, you can see that's terribly difficult to read. So I'll break it down like this. Instead of this will display gibberish, I'll do something like this. I'll break these down individually. So I'll just select the UID, which should be 1, right? Because it's auto increment. So select UID. There's 1. We could select SSN, and let's see what our SSN does for us. There again, it's in binary. Command line cannot read binary. What about our SALT that we named SALT, and we shouldn't do that in our production environment, but again, that is also in binary as well too. So that's fine and dandy, but then how do we compare these values if a user contacts a first level customer representative and they say, could you please give us the last 4 digits of your social security number, say? We could even include that as a value, right? So even the customer rep doesn't know the full social security number. They just know the last 4 digits, and we could store those 4 digits perhaps as a substring, or we could make another attribute with only the 4 digits of, last 4 digits of a social security number. Either way, you could hide the actual data and not allow a lower level customer representative to find out the full social security number. So what we do, gang, is this. Since we can't unhash or dehash a value, what we would do, the customer representative or associate would say, could you please give us the last 4 digits, or here in this case, we'll say, could you please give us the last 3 digits of your password, or 3 characters of your password, right? Or the last 4 digits of your social security number. Here it's the entire password. So the customer rep would say, okay, could you tell us your password? And by the way, sometimes you have to do that, right? If you're working with administrators, they'll say, well, could you please tell us your password? Well, even administrators won't see the password. So what they'll have to do is run this type of a query against the actual hashed and salted value. So what we're doing here is select the UID, select that user from the user table where the social security number is the binary version. That's what unhex function is doing. The binary version of our salted and hashed, or concatenated, of course, the concatenated salt attribute, the value for that, we're going to concat that with the actual password, and then it's going to be hashed at SHA-2 512 hash value, and then we're going to unhex that, and then if there's a match, it's going to show, if there's a match with our social security number, it's going to show, I said password, I meant social security number, it's going to show who the user is. So let's do that right now. And let's put this in here. And in fact, it does work, right? So based upon that concatenated salt, which is hashed to the secure hash algorithm 2 512 hashing algorithm, it was unhexed, put in binary to make a comparison to the actual value that's stored in SSN. It showed, in fact, that belongs to user 1. Okay? All right, gang. I hope this was helpful. If you do have any questions, please post them to the discussion board or send me an email. All right, you guys. See you all in class.